Assalamualaikum and greetings to all. Today's topic is on higher order partial derivatives. Okay, let's say you're given a function with two independent variables. Let's say z is f of xy, or a function with three independent variables. Let's say w is f of xyz. Then when you differentiate these functions, you get partial derivative. If you differentiate the functions more than once, then you have higher order partial derivatives. Okay, so here are the notation for second order partial derivative, meaning that you differentiate the function twice. So if you differentiate twice, then you get second order. If you differentiate three times, then you have third order and so on. So these are the notation for second order partial derivative. Okay, now let's look at the first one. This is the subscript notation symbol that we use, notation fxx, meaning that you differentiate function f with respect to x twice. But if you want to use partial notation, then this is the notation. We have partial square f over partial x squared, meaning that you differentiate f with respect to x twice. The second notation, this is the subscript notation for fxy, meaning that you differentiate f with respect to x first and then with respect to y. And this is the notation using partial symbol. So you have partial square f over partial y, partial x, meaning you differentiate with respect to x first and then y. And the third, we have f and then the subscript is yx, meaning you differentiate f with respect to y first and then x. But if you use the partial notation, it will be partial square f, and in the denominator we have partial x, partial y, which means that you differentiate f with respect to y first and then x. And here we have fyy, meaning you differentiate f with respect to y twice. Okay, so if you're using subscript symbol, subscript notation, the sequence of differentiation is from left to right. So if it fxy, meaning differentiate f with respect to x first and then y. But if you use the partial notation, the sequence of differentiation is from right to left. So here, if it's partial square f over partial y, partial x, meaning first you differentiate f with respect to x and then with respect to y. Okay, and of course, you can also use z instead of f because z is equal to f of xy. So you can use f or you can use z, because they represent the same function. Okay, now let's look at example. Okay, the first one, we have our function f is equal to x squared y e y. Okay, and then we want to find fxx, fxy, fyx, and fyy. So those are all second order partial derivative. Okay, before we proceed to finding second order, we need to find first partial derivative first. Okay, let's find partial f, partial x, or you can use this notation. Okay, alright, so we want to differentiate f with respect to x. You hold y as a constant. Here you can see that y, ey there, that is considered as constant, so you don't do anything, you just copy them. You just differentiate x squared, so that will give you 2x. So that's the first order. Now what we want is fxx. Okay, that's the second order, this one, the first one. Okay, what you do is you differentiate the first order, which is that, with respect to x again. Okay, so you differentiate the first derivative with respect to x again, then you have the second order. Okay, differentiate 2xy ey with respect to x again. Y ey is considered as constant. 2 is also a constant. Differentiate x, we get 1. So this is fxx. Okay, next, oops, what happened there? Okay, next is we want to find fxy. So for fxy, what you do is you start with partial f, partial x, and then you differentiate it with respect to y. Okay, you take partial f partial x, which is this, and then you differentiate it with respect to y. Okay, so partial f partial x is 2x y e y. Okay, so in this case 2 and x is considered as constant. Okay, so I'm going to write it before we differentiate y e y. And then for y e y, you can see that this is product of two functions. One is polynomial and the other is exponential function. So we have to use the product rule. Okay, so this one is u, let's say, and this one is v. Okay, let me erase that. Okay, all right. So so this one is u. This is u. And this one is v. Okay, now let's using the product rule, differentiate u, we get 1, and then copy v, then plus copy u, differentiate v, the derivative of ey is also ey. So from here we get, you can simplify your answer by factoring ey out, then you have 1 plus y. Okay, so this is fxy, the second order partial derivative. Okay, next we want to find fyx. Okay, so in order for us to find fyx, we need to find fy first, which is or you can write it as partial f partial y. So what we want to do now is we want to differentiate f with respect to y. So when you differentiate with respect to y, you consider x as a constant. So x squared there is considered as constant. So you just differentiate y ey here using the product rule. So that would be differentiate y, we get 1, and then we have ey. Copy y, differentiate ey, we get ey back. So we have that. Or you can simplify this by factoring ey out as ey times 1 plus y. So that is first order fy. Next is we want to find fyx, which means that we start with partial f partial y and then we differentiate with respect to x. Okay, so for partial f partial y, hang on, it should be x. Partial f partial y, we just obtain here. So we have x squared ey 1 plus y. Okay, so now we want to differentiate with respect to x. So when you differentiate with respect to x, we consider y as constant. So ey times 1 plus y there is considered as constant. So we only differentiate x squared with respect to x. Then we get 2x. Okay, so that is fyx. The next one is fyy. So for fyy, we start with fy, which is partial f partial y, then we differentiate with respect to y again. Okay, and from before, fy is this. Okay, we have x squared ey 1 plus y. Okay, so when you differentiate with respect to y, we consider x as a constant. So x squared there is whole as a constant. So we need to differentiate this bit here with respect to y, and then here you can see that we have to use the product rule. Okay, I'm gonna let's say this is our u and this is our v. Okay, now using the product rule, differentiate ey, we get ey, then copy v. Okay, and then copy ey u, then differentiate 1 plus y with respect to y, then we get 1. Okay, then we can factor ey out. This would be ey plus eyy plus ey. So we have 2 ey there. Okay, factor ey out, we get 2 plus y. Okay, so that is fyy. Okay, I'm gonna save example 2 there for our live class. Okay, I'm gonna go straight to the theorem here. It's called Euler theorem. It says if fx, fy, fxy, and fyx are continuous and defined in an open space that contains a point AB, then fxy at AB is equal to fyx at AB. So here you can see that the sequence of integration does not matter. You can differentiate with respect to x first and then y, or y first and then x. It will be the same, provided that they are continuous and defined in the open space that contain a point AB. So now if we look at our example, the first example I've shown you, this is fyx, where we differentiate f with respect to y first and then x, we get that. And here we have fxy, where we differentiate our function with respect to x first and then y, and you can see that they are exactly the same. Okay, so in this case fxy is equal to fyx. So the order or the sequence of differentiation does not matter, as the result will give you the same function. Okay, so example 2 here, we'll do this, we'll solve this in our live class. That's all for today. Thank you.